Next, we've got the integral of tangent x dx. This is not one of the basic integrals that we know, not one of the basic antiderivatives that we know. We know the derivative of tangent, and that would be secant squared, but we don't know the antiderivative of tangent yet. So perhaps if we wrote it in terms of sines and cosines, that would give us a hint of how to do it. So we have the integral of the sine of x over the cosine of x dx. So did that make it look easier or more difficult? Well, I would say it made it easier because now we have something to go with, something to work with. If we let u equal, really we only have two choices. We can either let u equal sine x or we can let u equal cosine x. And I'm going to let u equal cosine x. If you would like, you may try sine x, and you won't come up with anything good. So the derivative of cosine x is negative sine x. You'll see that I'm missing a negative, so I'll multiply by a negative, and I'll multiply by another negative. Now the whole numerator is my du, but the denominator is u. So I've got negative integral 1 over u du. This should look familiar to you, and this is the ln of the absolute value of u. We'll substitute back our cosine, and we have the ln absolute value, negative ln absolute value of cosine. Sometimes, if you remember from algebra, sometimes we bring that negative sign, that coefficient, up into the power and write our solution as the ln of the, what's 1 over the cosine? It is the secant of x. Don't forget your plus c. This next couple problems, we're going to use substitution, but with definite integrals. So what makes this a definite integral? Of course, it's got limits of integration, 0 to 4. It is important to note that our function is defined from 0 to 4. If we let u equal 2x plus 1, du is equal to 2 dx. Well, it would be great if we had a 2 dx. So now we have a 2 dx. So what does this become? We have 1/2 the integral of u to the 1/2 du. Now hold on. These limits of integration are x's. This says x equals 0 and x equals 4. But I'm not dealing with x's anymore. Now we're dealing with u. U has something to do with x's. So I need to know when x is 0, what is u? Well, substituting in right here in our u equals, if we set x equal to 0, u equals 1. If we set x equal to 4, 4 times 2 plus 1 is 9, u equals 9. By changing the limits of integration from x's to u's, that means that I will not have to go back to x's at the end of the problem. Because remember, when we evaluate a definite integral, we end up with a number. Evaluating an indefinite integral gives us a function, that is the antiderivative function. Evaluating a definite integral gives us a number. And since this is a positive function, think about the square root function, you can think of this problem as finding the area under the curve. Okay, so we integrate this, and we have 1/2 u to the 3/2 times 2/3. And then what we do is we write from 1 to 9. So this is the fundamental theorem part 2 from one of the previous sections. Notice I don't have to do plus c. I have some like terms that I can simplify. And now I'm saying 9 to the 3/2 power divided by 3 minus 1 to the 3/2 power divided by 3. 9 to the 3/2 power is 27, I think. Yes, it is 27. Divided by 3 is 9. 1 to the 3/2 power is 1. So 9 minus 1/3. I feel like maybe we did that problem before once. Is, what is that? 26/3. All right. Next problem, another definite integral. But this one, we need to pick what we want for u. Now, we're never going to just pick u equals x, because that would just effectively change the letters from x's to u's. That wouldn't help us out. We need something to get this to look like what we want it. Notice if I write the integral like this, that might help you see what's happening here. If we let u equal the ln of x, then du is equal to 1 over x dx. The derivative of the ln of x is 1 over x. So we have our du right there and our u right here. This gives us the integral from something to something of u du. Now, we have to update our limits of integration from x's to u's. If x equals 1, then u equals the ln of 1. The ln of 1 is 0. If if x equals e, the ln of e is 1. So here these are u's. And so this integral now is all in terms of u. There aren't any x's here anymore. The integral of u is u squared divided by 2 from 0 to 1 is 1/2. You can work out those details. 1/2 squared minus 0 squared. Last thing for this section is about symmetry. And symmetry kind of gives us a hint. Could make our life a little easier. It says, if f is continuous on the closed interval from -a to +a, and if f is an even function, that is, it has y-axis symmetry. Think a parabola, right? And you want to find the integral from -a to +a, what you can do is you can find twice the integral from 0 to a. So since it has y-axis symmetry, whatever you get over on this side is going to look the same on the other side because it's a mirror image there. So you can go from 0 to a and then double it. On the other hand, if you have an odd function, think like an x cubed function, that is origin symmetry, and you go from -a to +a, the integral is 0. You can think of it like this. This area over here is below the x-axis. This area above here is above the x-axis. We saw that net change theorem in the last section. These should look exactly the same if it's an odd function. So this negative area here just counteracts that positive area over there, and the area cancels out into 0. So here's your example. You mean you have to remember what trig functions are odd and which ones are even? Yeah. Well, I happen to know that the sine function is odd. The sine function is a continuous function from -pi to pi, and we're done. Since sine x is odd. Now, if this were the integral of cosine of x. The cosine of x function is an even function, so I could do 2 times the integral from 0 to pi of the cosine x dx. The integral of cosine x is sine x, and then sine at pi, cosine, sine at 0, cosine at 0. It looks like we get 2 times 0. Does this make sense? Well, let's think about what we have. Cosine goes like this. Here's pi over negative pi over 2. Here's pi over 2. Here's pi. Here's negative pi. What we're doing, we're actually going like this. So, turns out that the area from 0 to pi, this and this, were the same but opposite. And if you double that 0, this and this all cancel out. So that one also happens to be 0, but we use the even function property.